So I gave a talk about per title encoding at scale, because I was at video at scale. Really what I'm going to talk about briefly is just like, what is per title encoding? And really what I'm going to be doing is like, Netflix has thrown down per title encoding. They did this back in like December 2015. Sometimes they don't go into as much detail as I would like, and that's kind of what I'm going to be going over today. I'm going to talk to you a little bit about why it matters and give you some examples. I'm going to try and like explain, although not very well, practical approaches to per title encoding. I'm going to try and get some code up in a GitHub repo somewhere for one of these techniques that we really like, just so you can play with it yourself. And then I'm going to talk about our rad new approach for doing it with machine learning. Everything gets better when you throw machine learning at it, so that's why we did. And then I'm going to chat about what's next in per title encoding techniques. So what is it? Well, Netflix threw down this blog post, and really what they were saying is, fundamentally, there's no one-size-fits-all approach to encoding. Each piece of content you have, you need to analyze it and figure out what kind of content it is before you can determine how best to encode it. And Netflix talked about this convex hull of quality and bitrate curves forming the basis of how they do their encodes. And I'm going to try and visualize that with you a little bit. Here I've taken two clips. One of them is a very complicated piece of content. There's water, it's kind of like white noise. If anyone's familiar with compression, this stuff is really hard to get right. And then on the bottom is this really chill drone flying over a city. It's like a slow-moving static image, really low complexity content. I'm going to do a bunch of encodes at a bunch of different widths. These widths are taken from things like the Netflix blog post. I've also sprinkled in one or two from the Apple encoding ladder just for thoroughness. And I started at 200 kilobits and worked my way up in steps of 10% or 50 kilobits, whichever was higher. Sort of rounded up to 50 kilobits. So that gives us this really cool graph. So let's start with the high complexity one. I've used Netflix's VMAF score, which is the Video Multi-Method Assessment Fusion. Basically, this is really cool. It gives you a score between 0 and 100 of how well you did on your encoding, 0 being awful, 100 being great. And for this high complexity content, everything kind of makes sense, right? Down at the dark red area, we have pretty terrible encodes. Up at higher bit rates, we start getting into green territory, bluish green territory. And what I've highlighted in red on this graph is for each bit rate, which width maximized quality when I did that encode. And you can see that this takes like a little walk up through the colors, trying to go for the best color each time. And in case you're wondering if this is just an artifact of VMAF, it's not. You can use SSIM and get a similar shaped curve with a similar shaped convex hull, and you can use PSNR. The exact path wiggles a little bit between these, and you can see here that PSNR actually likes 720p way better than these other ones do. But overall, the technique remains the same. Now look what happens when we use our low complexity content and do a bunch of encodes there. The shape of the curve changes radically. Here, because our content is so low complexity, it never makes sense to use the lower resolutions at any bit rate. It starts bad, it ends bad, and what our data is saying is that you should start this content at a fairly high resolution, and you should move up to 1080p at 1.1 megabits. And again, this SSIM shows the same shape of the curve, although the values, I don't understand SSIM. I'm just going to level with you. These values don't quite do what but the shape, look at the shape. And PSNR has the same shape. So like this is, yeah, okay, it all makes sense, right? Now let's take a look at these two curves just flattened. You can see that these are the optimal encoding recipes, given my encoding parameters, given H.264 and 2pass and whatnot. But you can see that what it's telling us is these pieces of content are different, and you need to encode them completely differently if you want to maximize quality. Here, what I'm doing is taking bit rates and showing you which width maximizes the quality. And that's the first thing that we can do with this data. The other thing that we can do with this data is, given a resolution, we can maintain a target quality by varying our bit rate. That's kind of like doing a CRF encode. Or given it's not quite a CRF encode because it's a constant bit rate, but it's kind of like the same vibe, right? We want to maintain that quality. We have a target quality. And again, given a quality, we can minimize the bit rate if we want to by varying the resolution. We can pick You know, I want a VMAF score of 80, and we can choose which encode minimized bitrate, because we want to give our users, you know, a medium quality encode. Why it really matters for us at Mux is we're delivering HLS, and given a bitrate that we've picked based on the distribution of bit rates of our users, you know, we have a bitrate ladder. We usually try to pick like 7 bit rates that are going to do a good job for the users watching the content. We can maximize quality by varying our resolution. This is why we care. I've got some charts here. On the far, don't pay attention to the numbers too much. What I'm saying is, like, given a selection of video bit rates that kind of match the Apple fixed ladder, and given the static resolutions that Apple recommends, there's a little wiggle here because my bit rates didn't quite line up. These are the scores. But if we pick the best resolution, this is how much better we can do on our high complexity content. Here you can see that especially up at higher bit rates, we can do better than our static ladder by varying our resolutions, and in fact keeping them a lot lower than what otherwise would be recommended. The same thing happens with SSIM. The numbers are very small. They're not very impressive numbers. This is why I don't understand SSIM. The curve looked great, but these numbers don't. But PSNR looks good. PSNR, we're back. We're doing even better across everything. Now look what happens, though, with our low complexity content. We're doing fantastically well in VMAF, especially down at the lower bit rates where people are really struggling for quality. We can do a lot better by using these optimal resolutions as compared to the static resolutions that we might otherwise use. And in fact, we're moving up to 1080p at 2 megabits, which is kind of a little weird, especially for those of us using static bitrate ladders, but that's what it's saying that that piece of content needs. Same with SSIM, same with PSNR. Okay, so let's give an example. Here's a 1 megabit encode. On the right is the 720p that our model suggested we use. On the left is the static bit rate that Apple recommends you use. And hopefully you can see that the one on the right is a lot sharper. We've done a better job by choosing a better resolution. And likewise, kind of on the inverse, on the right is our 1080p encode at almost 6 megabits. But we're saving almost a full megabit without reducing the visual quality. These two videos are hopefully the same quality to you, otherwise I've done a terrible job. And you shouldn't actually be able to tell the difference between the much lower resolution and the higher resolution. Okay, so how do you implement it? Now that I've convinced you that you should do this, how do you do it? Well, option number 1 is you can use brute force. You can generate a set of encodes like I did, with a whole bunch of resolutions and bit rates, and then you can search through the space for your desired encoding properties. The pros of this approach are that it's parallelizable, it's pretty straightforward. You have a database and a bunch of jobs, and then when they're all finished, you can use that data. And the downsides are it wastes a huge amount of compute. My charts took like 350 encodes for those pieces of content, and you can imagine that for like an hour-long piece of content, this is not going to be practical for many encoding pipelines. The other option is to tightly walk the convex hull. You can start up at, say, 10 megabits, comparing 1080p with 720p, see which one wins, and then step down and do the next comparison. Here's a better explanation of what I mean. I start at 10 megabits, and I'm comparing 1080p to 720p. 1080p wins. I step down to 9 megabits, I compare 1080p to 720p. 720p wins, and I step down, and now I'm comparing 720p to 540p. This kind of works, and it's efficient. You only need to do, like, you know, you can pick your number of encodes that you want to test and the bit rates you want to test, and then you can do 2 or 3 encodes per bit rate. The downside is it does require good rate control in order to be able to do this. Things like X264 with a 2-pass mode where you're tightly hitting a bit rate are great for ABR algorithms and great for this comparison. But with newer codecs that don't quite have the same approach to rate control or don't quite have the same ability to give you a good predefined rate, this is quite a difficult thing to implement right. And it's obviously not very parallelizable. You need to do a full encode, 2 full encodes, compare them, and then step down to the next one. The third option, which we experimented with, but we couldn't quite get to work, but in principle you might be able to get to work, is to do something with an estimate. You can estimate doing something like an X264 CRF encode, which is like a constant quality encode. You can figure out how to map that into a space and how to change your curves based on that data. But as you can see here, I did a couple of encodes like CRF22 or CRF25, but like the resulting qualities that came out of those encodes, they kind of matched, but they kind of didn't. Like my CRF25 was not really a constant quality. The bit rates varied wildly. And you can see that, okay, it's 3 times the bit rate at CRF25 for our high complexity content, but it's not clear what you actually do with that information in order to maximize quality. So what we did is we cheated. We threw some machine learning at this. I teamed up with a data scientist at Mux. His pros are that he's a data scientist, but he's not a video engineer. But somehow, with our powers combined, we were able to build a pretty cool model. So we took 500 sample clips, and this was less impressive. When honestly, when Google's up on stage at Video at Scale, being like, "Oh yeah, we ingest like 400 hours of content a second," you're like, "What? What?" Okay, so like my 500 sample clips needs to go up to like 50,000 sample clips for our model to perform really, really well across a wide range of content. But we then took these clips, we walked their convex hulls, we tried to get a training set that was quite diverse by pulling in things like trailers, by pulling in things like ZIF, by pulling in things like some of our customers' data. They agreed to that. And then we tested 54 bit rates. We did 2 encodes per bit rate. We used VMAP, which is hella slow, and it took about 140 days of processing. And that's just the beginning. Really, we're looking at doing like 14,000 days of processing. But this is a good start. And in fact, it works really well. So how we built it, we leaned heavily on a concept called transfer learning, which is basically like taking a Google model and reusing it for something useful so that you don't have to spend thousands of hours. So we used Inception as our first layer. Inception is an image classifier, and we chopped off the top layer and threw it away. And then you get a vector representation of your image that's pretty useful. Then we trained a second neural net on the YouTube, thanks Google, YouTube 8M dataset, which is like 8 million classified videos, and we fed in frames from video that had been run through Inception and retrained that. And again, we trained a video classifier, chopped off its top layer, and used that as a vector representation of our video, before finally using an LSTM network. Based on that vector representation of our video, we can then turn that into an optimal encoding ladder. And we used an LSTM because the LSTM can take, I'm just going to sniff on this audio track, LSTM can take steps along, and it uses its previous prediction to make another prediction. That's a really useful property for us, because once we've decided to switch from 1080p to 720p, we really don't want our model to decide, actually, I'm going to go back to 1080p. That was the wrong decision. It's like, no, go with it, be monotonic, go down in resolutions. And we built it into Mux Video. This is live. It's behind a flag called per title encoding. It's significantly faster than real time, but not quite as fast as we'd like it yet. Our demo goes from being like a 5-second ingest to a 20-second ingest, which is kind of a bummer. And here's an image that my data scientist friend Ben tells me will help explain what we did. You can see there's some of the words I said. Right? There's a YouTube data set, a deep neural net, there's a convex hull data set that we created, an evaluation data set of some of the convex hulls we set aside to make sure we're not just fooling ourselves, and our LSTM that outputs our final predictions. And we're looking at constantly growing this with more and more data types. And the other really cool thing about this is, as new users bring to Mux new content types and are interested in using this, we can actually retrain our model on their specific content to do a better job of encoding it. So, as I said, it's live, and we'll even show you the encoding ladders that we're predicting. We're not, keeping this behind closed doors. We really want to spark a discussion about making this something that more people are doing. It's kind of crazy that this applies to H.264, and it's a codec from 2003. But it's taken us, at least, over 10 years to get around to actually really diving into some of the 15 years, to dive into some of this research. So what's next? Well, for us, more training data. 500 videos was actually good enough to do a really good job, which blew us away. We kind of put this model together as a test of whether or not we could even train something that would be useful. But the results we got were so great that we deployed it. We already have people using this in production. They've turned on the flag, and they're getting great results from it. So that's really exciting. But we would like to greatly increase our training set. That's something we're working on right now. We're looking at better performance, as I mentioned, especially for shorter clips. At Mux, I'm going to sell Mux a little. No. It's more like this thing we'd love to get it running in a few seconds. In principle, we can, but our infrastructure around it just isn't there yet, especially for the shorter clips where some of the overheads of TensorFlow, which we're using, kind of kill our performance a little bit. For things like an hour-long clip, actually, it does a really good job because we have lots of time to play with. And there's no reason this won't apply to things like VP9 and HEVC. We might need to do some tweaks to get it working with these codecs, but the same principle applies that given a bit rate, you still need to vary your resolution, even with these codecs, in order to maximize your quality. And we're thinking about open sourcing it. We kind of would love to get more people in industry testing out these techniques and ideally giving us feedback, trying our library, maybe tossing us a little training data. But please talk to us. We're interested in open sourcing it, but we don't want to be like stuck as the the one-star GitHub project that a couple people checked out and then left it to die. We're also working, as I mentioned, we're working on better bitrate selection. We see content type adaptation and per title encoding as being one half of a problem, and the other half of that problem is how do you pick bit rates that will actually match what your users actually have available to them. It would be great if we could just be Netflix and do like, okay, we're just going to do an encode at 5% increments starting at 200 kilobits and just offer a manifest that has 200 different renditions in it, but that's not practically cost effective for our users. So we are doing some research next on how to better select bit rates. And finally, everything I just said applies to per scene, not actually per title. This is one of the rad new things we found is like, imagine that your video is someone in those rapids followed by the drone footage, and that's your scene, that's your title. In order to maximize quality for that title, you need to be willing, mid-rendition, to switch resolutions. And in fact, we're looking at just removing resolution from our HLS manifest. It's not useful. It is not useful information. If you have a bit rate, then you are saying, I'm going to target that bit rate. There should not be a corresponding resolution. You must allow it to vary over the length of your clip in order to maximize the quality that users are seeing. And this makes total sense because we already do it. As bit rate fluctuates, ABR algorithms and ABR players have to be able to switch resolutions on the fly and seamlessly to deliver a great experience. That's what we're going to have to do per rendition. Finally, here's a little clip from a trailer, and hopefully you can tell which one is encoded with our new settings. This is actually like our model predicted that at 1 megabit, this scene would look great. I'm just going to play it one more time. This scene would look great at 1080p. I took a center crop and put it side by side and encoded it with a ton of bits. And you see that, yeah, it really does look better if you use this crazy high resolution because it's a fairly chill scene. Thanks for listening. And yeah. And I apologize to the people who heard that twice. Yeah, any questions, I guess? So the CEO of Mux and I, just for the record, have discussed open sourcing a little command line utility built on top of TensorFlow that you would point at an MP4, and it would give you a JSON blob that says, if you want to use this bitrate, you should probably use this resolution. And if you do that, you'll probably maximize quality. Great question. We need to make FPS an input. We're also struggling, not to say struggling, we got great results from the simple model. We are investigating, and we haven't yet found a good way to include motion information. Motion information and FPS kind of go hand in hand a little bit. Right now, we are optimizing this model for 30 FPS content / 25 FPS content. It works great for. Higher FPSs are a challenge. They probably require, so actually VMAF itself, our primary metric, came out of Netflix, is a really useful metric. We've gotten really great results from it, and it only makes sense at 30 FPS or 24 FPS. It does not make sense at like 60 FPS. The model is just not trained for that. That's a challenge. We're hoping to lean a little bit on the community for some of that stuff. is my best answer. But actually, the model works pretty well still. So yeah. What I showed was that these two clips are radically different. And you need to treat them completely differently when you're encoding them if you want to maximize quality. Let's take a 2 megabit encode. For the bottom scene, you should use 1080p. For the top scene, you should use something like 640p, the 960 by 640. That means that if you get a title into your system that is one clip followed by the other, and that's the video you're trying to maximize quality on, right now, what we do is we split the difference. Our model will take frames from the first scenes and the second scenes and kind of average them out into something in the middle. Usually it'll use like, in this case, maybe 720p. That will improve the quality of both scenes. So it'll decrease the quality of one scene a little bit and improve the quality of the other scene a little bit, depending on where you like tilt the scales. But in order to maximize quality at 2 megabits, you should probably deliver to your users for the first clip, 1224 by 960 by 640, followed by like an HLS discontinuity, followed by the next scene. So what we're looking at being the future is running scene detection on all of our clips. There's some really exciting research coming out of Facebook that was spoken about yesterday around creating really good scene detection algorithms, not just per shot and not just like where are the keyframes, but like deeper than that, especially around crossfades. And we're looking at leveraging some of that and delivering manifests that just at 2 megabits will change resolution according to the content type that's in those chunks at that time. Yeah, so like we can, with this, for example, we can see for this clip where you should place your encode. But what you'll notice is these are, the bottom one is a single scene. The top one is a single scene of the same content but from different shots. But overall, it's very, very similar in complexity. But yeah, switching resolutions at 2 megabits would maximize the quality that a user was seeing if they watch this content. And in fact, keep the quality as high as possible for them there. So we're looking at figuring out what the support for that is going to be and maybe tweaking how we interpret some of the standards. On 84% of our training set of 50 clips, we improved quality. On about 5% of them, we slightly reduced quality, and the rest it was a wash.
And that's on the holdback from machine learning, or that's on the training set?
That is on the holdout from the machine learning. We cut those clips out and used them as our validation set. And that was the reason we decided to actually make this public. Because basically, on some of the clips, the improvement is like the data I showed here, like for our high complexity stuff, at a lot of the bit rates, it's a mild improvement, but it's still an improvement. What we found is that users were coming to us with content types like screen recordings, and our fixed bitrate ladder for those screen recordings sucked. But with this model, it was detecting, hey, this is really static content, it's really consistent content, switch up to 1080p at 1 megabit. That's going to make this look best. And we've done that. We have users in production with this flag set to true because it makes their content look better. What we haven't found is sort of really high complexity content yet, where going lower makes a lot more sense, but we do have those clips in the validation set. Here. So this was our overall results, where you can see that we're doing, and this, yeah, compared to the standard ladder over a bunch of bit rates, we are getting better. This is kind of a little misleading though, because there's a whole bunch of videos where our predicted ladder and the Apple ladder, yeah, it's kind of a wash. They both do a good job, but there are content types where this difference is huge. They're getting like 15 VMAF points higher by using this, and those weren't in our holdout test set. So this curve is not, it doesn't look visually really impressive. Like you can like plot like an AV1 curve in here and you'll be like, wow, you can go all the way down to 200 kilobits at 720p. And it's like, but this is like more subtle, but for some of our users, a huge improvement. And please check out the blog. We're trying to be pretty open about this one. Getting people to trust our encoding is like really important to us. Mux has live around the corner. We haven't launched it. We are investigating how these techniques will apply to live. The best kind of approach we have right now is to use this technique on a per chunk basis and apply it one chunk later. So we're going to miss that transition between high complexity to low complexity or low complexity back to high complexity, but then we'll get it on the next chunk. That's kind of where we're seeing this, and that's one of the reasons we want to try and improve performance even more. For low latency live, putting a machine learning step in the loop like this, like our model, is probably not going to work. We're probably going to need to tweak that model and simplify it, and what you'll probably need to do is pre-train content type classifiers on your content. A great example would be a football game. There's players on the field, followed by talking heads, followed by ads, followed by back to the field, and each of those is probably going to need a different encoding ladder. What we're thinking about it as is pre-training a model that can map from a frame type straight to a convex hull without requiring multiple frames. So you can just be like, are there talking heads? Yes. Okay, use the talking heads model. Is it players on the ground? Yes. And you can do that in milliseconds as opposed to our model, which does take several seconds and can really harm your performance of your live stream.